So we start talking about rotational equilibrium. If multiple torques act on an object in a way that they cancel each other out, the object is in rotational equilibrium. It's not rotating, or it's rotating at a constant angular velocity. This looks a lot like equilibrium when we talked about forces. The sum of all the forces is equal to zero, and in fact it's the same type of concept. In this case, the sum of all torques is equal to zero. What this means is we can add a third condition or a second condition to objects that are in equilibrium. The sum of all the forces has to be zero in that object, but the sum of all the torques also has to be zero in that object. This is actually a set of equations which is really important in the engineering field. Anytime you're doing a problem dealing with statics, you're dealing with rotational equilibrium along with regular equilibrium, or force equilibrium. So let's look at an example here. I have two blocks that are sitting on a solid uniform beam. In the middle of the beam is supported by a fulcrum. And one is a 10 kilogram block and another is a 5 kilogram block. And I know the 5 kilogram block is 6 meters away from the fulcrum. And I want to figure out how far does the 10 kilogram block need to be so this thing is in rotational equilibrium. Well, if you look at the force that's acting on the beam, well, we have mg for the 5 kilogram block and mg for the 10 kilogram block. Sum of torques equals zero, then mgr, looks like this will be a counterclockwise torque, minus mgx, a clockwise torque, is equal to zero. The g's cancel out, and we could say mr minus big mx, and we can actually calculate that out and find that x has to be 3 meters. Now, hopefully that wasn't all that surprising to you that we got 3 meters. If something is twice as heavy, we'd expect it to be half as far from that balance point, that fulcrum. Another way to write this is to say that the sum of all the counterclockwise torques is equal to the sum of all the clockwise torques, rotational equilibrium. So here's another example problem that's a little bit more complicated that deals with equilibrium. Sorry, got a little tickle in my throat. So I have a firefighter with a weight of 875 newtons climbing up a uniform ladder with a weight of 450 newtons that's positioned at an angle of 50 degrees above the horizontal as shown in the diagram. It says the ladder is 8 meters long and the firefighter is currently 6 meters up the water, and that the wall is covered in ice, so there's no friction between the ladder and the wall. And it wants us to find the forces that the ground and the wall exert on the ladder. So the first thing I'd want to do in this type of problem is try to figure out where are all the forces that act on the ladder. Well, we obviously have the weight of the firefighter, which is here. We have the weight of the ladder itself, and I'm going to put the weight of the ladder in the middle of the ladder. Reason for this is if it says that it's a uniform ladder, what that means is that all parts of this ladder are the same weight. It happens to work out that you can make a simplification of, instead of saying, well, the weight of this part of the ladder and the weight of this part and the weight of this part, if it's a uniform object, you can put the weight of that object in the center of that object. That's what's called center of mass. We have a normal force acting on the wall, on the ladder from the wall, and we have two forces acting here. There has to be a frictional force, or else this ladder would just slide along the ground, and there also has to be a normal support force. So in order to solve this problem, I want to find NW, NG, and FG. I have three equations that I could use: sum of forces in the x equals 0, sum of forces in the y equals 0, and sum of torques equals 0. So if I tried to do this without rotation equilibrium, I have Fg minus Nw equals 0, sum of force in the x direction. Ng equals Wf minus Wl equals 0. So I could solve for Ng right now, but I have two unknowns here that I can't solve for. So I need to do sum of torques equals 0. And the first thing I want to do when I do sum of torques equal to 0 is I want to pick an axis of rotation. And I could technically pick anywhere along the ladder if this ladder is stationary, which it is, or not rotating. Probably the most logical place to pick an axis of rotation is to pick it where the majority of unknown forces are acting. So in this case, at the point of the ground and the ladder, that point of contact. What that means is that the radius for WL is 4 meters, this radius is 6 meters, and the radius for NW is 8 meters. What that means is I could say the torque from NW minus the torque from the weight of the firefighter minus the torque from the weight of the ladder equals 0. Now this has to be a clockwise torque, counterclockwise torque, and these two have to be clockwise torques. So I could actually now solve out well, solve out the normal force from the ground on the ladder. It's 1,325 newtons. That's because it's just the weight of the firefighter plus the weight of the ladder. I know that these two forces are going to be the same, so if I can solve for this force, I've also solved for that force. So that's where I'm going to go here. That normal force times L, the length of the ladder, times sine of 50 degrees, that angle would be a 50-degree angle, minus weight of the firefighter. Well, 6 meters up a 8-meter ladder, that's 3/4 times L, and then this angle has to be a 40-degree angle in here, minus WL, the weight of the ladder, L over 2, 4 meters up an 8-meter ladder, halfway up L, also sine of 40 degrees. And in this equation, the only thing that I don't know is NW. So first thing I did was I divided the L and I added the negatives over to the other side. Looks like divide everything by the sine of 50. If I plug in my values, I get the normal force here has to be 739.5 newtons. Basically what that's doing is preventing the ladder from rotating through the wall. What that means is that the frictional force also has to be the same. If that frictional force is not the same, well, this would slide out and the ladder would slide down. And so we can actually use all three of these equations to solve an equilibrium problem. So that's kind of a quick overview of rotational equilibrium and the types of problems that you can actually solve out using sum of torques equals 0.